So, control systems are basically it may be an electrical control system or mechanical control system, thermal control system, pneumatic control system, etc. We give some attention for electrical system and also mechanical system. Now, I am talking about system, electrical system, open loop system, mechanical system, etc. The main components of electrical system are passive elements and active elements. Passive elements are resistor, inductor and capacitor because they allow the current. Current is passed through them and they receive energy from the source and they are called passive. Active elements are the elements which give energy. Let us consider a simple RC circuit. This is excited by some input, say R of S, and C of S is the output across the capacitor. Say it has R and C, and a current is expected to flow when if this is a voltage signal. Now, we call this as a circuit because current flows and it is a circuit. Now, this particular one, when should I call it as a control system? Let us see, apply KVL to this simple loop. Okay. You can consider this as Vi of S for time being, and this is an output V0 of S. So, let us apply KVL to this. Ri plus 1 by C integral I dt is equal to Vi, equation for the first loop, and output voltage V naught is 1 by C integral I dt. If you apply Laplace transform to these equations, Vi of S, you get Ri of S plus 1 by Cs into I of S. Output voltage V0 of S is 1 by Cs into I of S. Now, if I want to get a transfer function of this RC circuit, V0 of S by Vi of S, this is equal to 1 by RCS plus 1 you get. This RC is the time constant of the system. Time constant of the system, it is represented by tau S plus 1, 1 by tau S plus 1. Now, this I can rewrite as 1 by tau into S plus 1 by tau. This is V0 of S by Vi of S. Now, the same circuit I can represent this way, a system. I was calling it as a system with transfer function of 1 by tau S plus 1 given by an input Vi of S and V0 of S is the output. Same circuit can be represented in a control system language as 1 by tau S plus 1 with some input and then some output. So, this part is a transfer function. This one and this one are same. As you know that you call it as a circuit, I call this as a control system whose components are R and C, and it is represented in time constant tau, where tau is equal to RC. What is its significance? We call it is a time constant, it is given by RC. What is its significance? I would like to see the significance of time constant. It is generally called, it is related with time. So, how much time the system is taking to give a response? How fast the system response is being known from time constant. For example, if I want to call this V naught of s as controlled output, suppose C of s, input as reference R of s, then this C of s by R of s is 1 by tau into s plus 1 by tau. So, to understand the significance of time constant, let us consider the reference input as impulse signal. As I mentioned, the impulse signal is very undesirable signal because it has a very high magnitude in short duration and whose Laplace transform is 1. Thanks to impulse, because impulse, Laplace transform of impulse input is 1. If you substitute R of s is equal to 1 here, the C of s will not change because it remains like this, because R of s is 1. So, I can say that C of s is the response for impulse input given by 1 by tau s plus 1 by tau. Now, if I want to see this response in time domain, let us apply inverse Laplace transform. So, C of t you will get by applying inverse Laplace transform to this is 1 by tau e power minus 1 by tau. So, you can see now the response in time domain 1 by tau e power minus 1 by tau is the response of the system for impulse input. So, this response can be drawn in the graph. C of t is the response and time response because it is with respect to time. Now, this response I want to plot on the graph 1 by tau at t equal to 0 and this is t by tau. So, this response will decay to 0. Impulse response will decay to 0 as time approaches infinity. So, I can say that this RC circuit represented by this system excited by an impulse input has like this. I say that it is a stable system because impulse response decays as fast as possible. It depends on what? It depends on tau. The time constant is nothing but R and C. For the values of R and C, different values, this impulse response may be like this, indicates that how fast or how slow the response is reaching the desired. Because impulse is undesirable, so I want to know that impulse response must decay as fast as possible, then I say it is a stable system. So, the information you get here for impulse input of an RC circuit is exponential decay, and then finally it reaches 0 as fast as possible. It depends on the time constant. So, this RC circuit, if you say R is equal to 1, C is equal to 1 farad, then the C of s by R of s of this is 1 by s plus 1. Because time constant is 1, I just assumed the values both 1, so time constant is 1. So, 1 by s plus 1, the denominator, it represents the pole, and in S plane this pole can be located here at s is equal to minus 1 sigma j omega. It is S plane, a complex plane, and the pole is located here at s is equal to minus 1. So, this is the language of control system in the form of poles and zeros, and the stable region in the S plane is the entire left half of the S plane imaginary axis is a stable region and right half of the S-plane is an unstable region. So, this particular pole in the left half of the S-plane, such a system is excited by an impulse input. You have seen the response exponentially decay. So, it is a stable system. Location of poles in S-plane will indicate the stability of the system and how fast the system is approaching the desired output. So, if the same pole, for example, so I can say that here C of S is equal to 1 by S plus 1 for impulse input. So, pole is here in the left half, so the response is decaying as time approaches infinity. Suppose C of S is equal to 1 by S. What does it mean? That the pole is located at origin. The pole is located now at origin. So, what kind of response you get? Means C of t is equal to 1. Means a response of this kind. It does not decay to 0. So, if the pole is located at origin, the impulse response is constant and it will not decay to 0. So, it is close to the verge of stability. So, I can say that it is a marginally stable system. Now, if the same pole, for example, if C of S is equal to 1 by S minus 1, means the pole is in the right half of the S plane. Pole is in the right half of the S plane, somewhere here at S is equal to plus 1, then the response C of t is you get as E of plus t, then this response will exponentially increase. It is an unstable system. So, try to understand the difference between these three figures, that pole in the left half is a stable system, pole at origin is marginally stable, and pole in the right half is an unstable system. So, the poles will decide whether system is stable or unstable. As I indicated that transfer function is a ratio of Laplace transform of output to the Laplace transform of input with the initial conditions ignored. So, that is the limitation of transfer function, that initial conditions cannot be considered. So, the standard form of transfer function is represented by C of S by R of S. This is called time constant form of the transfer function. It involves constant, then numerator terms and denominator terms. And here the denominator terms are called actually poles, and numerator terms are called zeros. So, the same function can be represented by in this form. This form is called pole zero form of the transfer function, and this is time constant form of transfer function. So, how are the poles defined? How are the zeros defined? So, these are called zeros, Z1, Z2, etc., they are called zeros of transfer function, because at s is equal to minus z1 minus z2 the given function becomes 0. Function becomes 0 at all these z1, z2 and so on. So, it is called 0, and p1, p2 etc., they are called poles, because at s is equal to minus p1 minus p2 and all the function becomes infinite. So, it is called pole. Now, this is the way generally we use in control system, either in pole 0 form or time constant form of the given system. Significance of time constant, I already indicated that how fast the system is responding for the desired output. Now, let us consider another example of an electrical system. RLC circuit. So, here as we have seen in the previous example, there was no L, there was no inductor, but here you have added inductor. So, energy storage elements, if they increase, the order of the system also will increase. Now, if I want to know the transfer function of this electrical system, I can write the equation by using KVL for this loop and also output equation in terms of capacitor. So, I get the transfer function V0 of s by V of s. Generally, it is represented by C of s by R of s. I will get as 1 by LCS square plus RCS plus 1. So, you get the transfer function. You can see that the denominator is actually called a characteristic polynomial. If you equate it to 0, it becomes the characteristic equation. The characteristic equation, the denominator 1. So, the roots of that characteristic equation must lie in the left half of the S plane for the system to be stable. Now, let us consider the example, this particular one with R is equal to 0, L is equal to 1, C is equal to 1. If you substitute these values in this particular function, it leads to 1 by S square plus 1, because R is equal to 0. So, 1 by S square plus 1 is the transfer function of this electrical system. Now, substitute R of s is equal to 1, because I want to know the impulse response of this particular system C of s for R of s is equal to 1, because it is impulse response I want to see. So, C of s is equal to 1 by S square plus 1. Now, if I want to see the response for this impulse input, I must apply inverse Laplace transform to this. It will be sin t. So, inverse Laplace transform of this function is sin t, and if you see the response, sin t is this way. This is C of t, and what do you understand from this response? The impulse response has sustained oscillations, means is not a good system. It is now, I can say that it is a marginally stable system with R equal to 0. Now, if we substitute R equal to 1 in place of 0, then the function becomes, what will happen to the function with R is equal to 1, L is equal to 1, C is equal to 1, the C of s becomes 1 by s square plus s plus 1. You get, if you get the roots of this denominator characteristic equation, you get complex conjugate poles. If you see this 1 by s square plus 1, the location of the poles in S plane are exactly on imaginary axis, because s square equal to minus 1 and s is equal to plus or minus j1. So, the two roots in the S plane for this function are on imaginary axis. Such a system excited by impulse input will have sustained oscillations. So, system is at verge of instability, because as I said, left half of the portion is a stable region, right half of the portion is unstable region. So, at the verge of stability and instability, the poles are located. Now, with r equal to 1, if you see that you will get a function like this, and if you solve for the roots of this equation, the poles will lie in the left half, of the S plane. And if you see the time response of this function c of t, there will be an exponential term, and that impulse response will be like this. Compare the difference. Addition of resistance in the circuit has oscillations exponentially decay, is a good sign, when compared to this one, and I can say that it is a stable system, means impulse response has decaying oscillations, not sustained oscillations. So, it is a stable system with r equal to 1. Now, suppose if you have a poles in the right half of the S plane, both complex conjugate, but they are in the right half of the S plane, say here, in the right half of the S plane, then if you see the time response of this, it will have this way. Now, you can observe the difference with poles on imaginary axis, sustained oscillations for impulse input, poles in the left half, decaying oscillations, and poles in the right half having exponentially increased oscillations. So, this is an unstable system, this is marginally stable system, and this is a stable system. So, the poles of transfer function or the roots of the characteristic equation will decide whether the system is stable or not. To consider the stability, I have taken the example of impulse input applied to the second order system, and then decaying oscillations exponentially indicates that it is a stable system.